Good evening, friends. My name is Pankaj Dunka. I'm Assistant Professor in JP University of Engineering and Technology, Guna. So, in last video, we have discussed how to derive SFE, that is steady flow energy equation. We have also discussed that when to use SFE, that is when multiple fluid streams are entering or when single fluid stream is entering. So, what should be the type of SFEE what should be the type of SFEE you will be using for these two cases. Now let us discuss some of the practical applications of this SFEE or how to use this SFEE to solve practical problems. So first let us consider a case of nozzle. Now nozzle is a device which is used to increase the velocity of the fluid. Let us say that we have a nozzle, a converging diverging type of nozzle, a generalized case, and let us say that this is adiabatically sealed so that no heat can leave or enter this nozzle. Now fluid is entering from this end and it is leaving from this end. Now to apply your SFEE, you first have to consider a control volume. Let us say that this is my control volume. Now applying SFEE. So before I apply SFEE, I would like to mention here one thing, that a single stream of fluid is entering or leaving. So the best way is to use per unit mass basis SFEE. That is energy which is entering here, or in expanded form, HI plus VI square by 2 plus GZI plus the amount of heat transfer. Firstly, writing this equation in its full form, then it is equal to HE plus VE square by 2 plus GZE plus W. Now you know that this is a no flow device. This is a no work device. That is, no work interaction is taking place, no heat interaction is taking place, as we have considered this as adiabatic. And at the same time, if we neglect the changes in kinetic and potential energy with respect to these, if we neglect the changes in potential energies with respect to the other terms, and at the same time we say that the inlet velocity of this, the inlet velocity to the nozzle is very small in comparison to the exit velocity, then what we can say that HI will be equal to HE plus VE square by 2. So this VE will be under root 2 HI minus HE. The thing which has to be keep in mind here is that we have neglected the inlet velocity. We have also assumed that there is no heat transfer in this. So how we are getting this velocity, increased velocity? We are getting this increase in velocity because of the drop in enthalpy, or in other words, kinetic energy is increasing at the expense of enthalpy. So the inverse or reverse of this nozzle is diffuser. So diffuser is that device where the pressure is increased at the expense of kinetic energy. So now discussing the next application. So this will be your turbine, let us say. So turbine is a work producing element, work producing component, machine. So let's say that this is my schematic of turbine. Fluid is entering from this end, it is exiting from here, and this turbine is adiabatically sealed, and it is transferring a work WT. So writing my SFE per unit mass basis again and expanding it, you can write HI plus VI square by 2 plus GZI plus Q dot is equal to HE plus V square by 2 plus GZE plus WT. Now this is perfectly adiabatic, so this will be 0. Neglecting changes in kinetic and potential energies, as they will be having a lower magnitude than enthalpy, let us say, then we will get this WT will be HI plus HE. That is, in turbine we get work at the expense of enthalpy. Enthalpy decreases or pressure decreases, and because of that we get turbine work. But the thing which has to be remembered here is that it is not always true that we keep these terms velocity and kinetic energy or potential energy term to be 0. It depends on the demand of the problem. If problem says that you have to consider them, then you consider. If not, then remove them. Now, third device can be thought of as my throttling device. A throttling device is that device which obstruct the flow passage, such that the pressure drops. And we assume that this device is adiabatically sealed. There is no drop, there is no loss of energy in the form of heat from the device or to the device. In previous case, this was my control volume onto which I have applied, and now let us say that this is my control volume where I am applying SFEE. So what I can do here is applying energy equation between these 2 points or onto this control volume. I will get HI plus VI square by 2 plus GZI plus Q is equal to HE plus V square by 2 plus GZE plus shaft work. Now this is an adiabatic device, no shaft work. Neglect the potential energy changes and assume that the velocities are very small. They are in very small ranges. So what I'll get, HI is equal to HE. So some people used to define throttling process is that process which is done in a zero work device in a adiabatic environment where the enthalpy remains constant. So this enthalpy constancy is the inherent characteristic of a throttling process. But mind it, throttling process is not a reversible process, it is an irreversible process because of the internal dissipative effect existing here. Now we can also apply our SFEE to other cases. Let us say a case of mixing. Let us consider a case of heat exchanger. Let us say that this is my heat exchanger. This is my heat exchanger. Fluid A is coming from here and leaving from here, and fluid B is coming from here and leaving from here. Now, let us say the entry point of fluid A is IA and the exit point of fluid A is EA. Entry point of fluid B is IB and exit point of fluid B is EB. Friends, in this, one of the fluid will give its energy to the other fluid. So let us draw the control volume where we are interested in, where we want to apply our steady flow energy equation. So if the flows are steady, so I can say m dot IA will be equal to m dot EA. That means the rate at which the fluid A enters is equal to the rate at which the fluid leaves. A leaves. At the same time, the rate at which fluid B enters is equal to the rate at which fluid B leaves. And let us say this is m dot A and this is m dot B. So we know that sigma E dot I plus Q dot is equal to sigma E dot E plus W dot. This is my steady flow energy equation, general sense, where the multiple streams are entering and multiple streams are leaving. In this device, there is no external heat loss. Whatever interaction is taking place, it is taking place between fluid A and fluid B. So this external interaction from environment, the external interaction of this control volume from environment is, in terms of heat, is not there, as well as in terms of work is not there, so as no shaft is there. So this equation gets simply reduced to EI is equal to sigma EE. So two streams are entering. So in this, two streams are entering. So what we can write here is m dot IA HIA plus VIA square by 2 plus GZIA for this one, and another one is entering from here. So m dot IB HIB plus VIB square by 2 plus GZIB plus, there is no heat transfer, so no plus, equal to this term, that is m dot EA HEA plus VEA square by 2 plus GZEA plus m dot EB HEB plus VEB square by 2 plus GZEB here, like this. If I neglect all the potential energy changes, at the same time I say that the kinetic energy contribution in this total energy is very small in comparison to the enthalpies or pressure energies, then what I can write here is m dot IA HIA m dot IB HIB is equal to m dot EA HEA plus m dot EB HEB. But friends, you know that the flow process is steady. M dot IA is equal to m dot EA is m dot A, and m dot IB is equal to m dot EB is equal to m dot B. So combining this and writing this as m dot A HIA minus HEA, and combining this and writing this as m dot B HEB minus HIB. So this is my energy equation for this control volume, and this says if fluid A releases its energy in the form of heat, then fluid B gains the same energy in the form of heat. That means the energy interaction. This is sometimes also called as adiabatic heat transfer. This is also called as adiabatic heat transfer. Now some people are very much confused in the sense of energy and mechanical energy. Friends, the term P by rho plus V square by 2 plus GZ is equal to constant. You all know this as Bernoulli's equation. This is a very well-known equation, Bernoulli's equation, given by Leonard Bernoulli or Daniel. I think it's given by Daniel Bernoulli, a friend of Leonard Euler. Now look this equation. Here this is kinetic energy, this is potential energy, and this is pressure energy. All the mechanical energy terms. So what is Bernoulli's equation basically? Bernoulli's equation is the mechanical energy conservation equation. It says if fluid is flowing from this point to this point, then mechanical energy here will be equal to mechanical energy here, provided there is no dissipative effect existing here, there is no friction existing here, and this is adiabatically sealed, and the fluid which is flowing is incompressible. But if you compare this with Okay, let us write this in differential form, in change form. So this plus v square by 2 plus gz, it will be this will be what? Constant 0. But if we write our steady flow energy equation in this form, so what? So let us derive steady flow energy equation in differential form. You all know that steady flow energy equation can be written like this: Q is equal to HE minus HI plus V square minus VI square by 2 plus ZE minus ZI into G plus W shaft. You all know this. Now if you differentiate it, you will get that TH plus VDV plus GTZ plus W. And now if you write this dq as du plus pdv, and h, we all know it is u plus pv, so on differentiating, this h will become du plus pdv plus vdp, that is du plus pdv plus vdp, and rest is the same. So this thing will go, and at the expense, at what is left, it is vdp plus vdv plus gdz plus dw shaft. So if you integrate this, and try to find out the change, then you can write W shaft is change in U plus PV plus V square by 2 plus GZ. So friends, at the first point you have this, at the second point you have this. They both look similar to you in terms of these mechanical energy terms, but the difference lies here. And this difference is because of, in real fluid we have viscosity, we have resistance, dissipative effect is there, friction is there. So if you account for everything, so this internal energy term will come. So this SFEE is basically for a real fluid. This is a general equation. But if you look this Bernoulli's equation, this is restricted only to a frictionless case, incompressible fluid case. So this is the difference between a mechanical energy equation and a energy equation. Now coming to unsteady flow energy equation. What is unsteady flow energy equation? Now what is unsteady flow? Unsteady flow is that flow where the properties changes with respect to time at any point. So if I am talking of this control volume, where some fluid is coming in, some fluid is leaving in, and this is my control volume, then the first thing is that as the process is unsteady, so this control volume can store mass or can release mass. That means the mass in this control volume will never be a constant for an unsteady case. That is, the rate of change of mass in this control volume is, which is m dot I if this is inlet and this is exit, minus m dot E, and this will not be 0. No, this will never be 0 because this is an unsteady case. Likewise, if this is interacting with universe with this Q and this W shaft, what I can write here is, I can write that the rate of accumulation of energy in this control volume will be equal to the amount of energy which is entering in this control volume minus the amount of energy which is leaving this control volume. So this is my unsteady flow energy equation. That is, net rate of accumulation of energy in the control volume will be equal to the energy which is entering in the control volume, total amount of energy which is entering in the control volume minus total amount of energy which is leaving this control volume. Now, this equation can also be written this equation, this unsteady flow energy equation can also be written like this. That is, energy which is entering in the control volume, plus energy in the control volume prior to the start of process, plus the amount of heat transfer to this control volume during the process is equal to energy which is exiting from this control volume plus energy in the control volume after the process has stopped plus the amount of work transferred from this control volume during the process. So this is what we will get if we integrate this equation. That means on the basis of initial and final, two states. And this is the rate that how energy is changing at any instant in this control volume. So both are important and you should know them by heart. So let us discuss one problem at the before finishing this lecture. And dear friends, this problem has been asked in many competitive examination and as well as in a year 2011 in engineering service examination. And this problem says that consider a duct where the pressure is Pi, temperature is Ti, and the fluid is flowing in this duct with this pressure. This duct is connected to a adiabatically sealed vessel initially where the pressure is P1 and temperature is T1. Now, this duct, this pipe which is connected with this vessel is of infinite capacity. That means its pressure and temperature will not change if we draw few amount of gas from it. And the gas which is in this chamber whose volume is V is same as the gas which is flowing in this. So you do one thing, you consider a control volume whose entry is this. And the question is, what will be the final temperature of this gas in this control volume if the filling process stops when the final pressure in this chamber is equal to the pressure in the pipeline. Now before I start solving this problem, I would like to tell you something about this equation or the equation which we have derived here. This. Here these E1 and E2 are the energies of the control volume which is static. So remember, E1 or 2, whatever you say, will always be written like this: U V square by 2 plus GZ. And EI or E, as they are energy which are coming to the control volume or leaving the control volume with the mass, so they will be H plus V square by 2 plus GZ. Because when the fluid is entering or leaving, it has to push its next layer to move in or to move out. That means it has to do the flow work, and that flow work when considered with this internal energy gives you this enthalpy. So that's why when fluid stream is entering or leaving, H comes. When we talk of control volume, so this is the energy. So friends, coming back to this problem, writing down this unsteady state energy equation for this case, for initial and final case. Now this is adiabatically sealed, so heat transfer will be 0 as well as work transfer will be 0 as there is no shaft. Now from this control volume there is nothing leaving out, so this is the case. So my energy equation gets reduced to EI plus E1 is equal to E2. If I neglect changes in kinetic and potential energy, so I can write this as mass entering into HI plus mass in the control volume at the start into U1 is equal to M2 U2. Now, before I start solving this energy equation further, remember one thing. Before you start solving any equation like energy equation or momentum equation, the first and foremost thing you should solve for is the mass conservation. Because if the mass conservation fails, then there is no there is no point in solving any of the equations at that particular either flow situation or energy transfer or interaction situation will be a fraud. It will not be possible at all. So firstly solving for mass conservation, and mass conservation says the amount of mass which enters in this control volume at the end, or the total amount of mass which enters in this control volume plus the amount of mass previously there in the control volume will be equal to the amount of mass at the end of this process in the control volume. So replacing this Mi by M2 minus M1 Hi plus M1U1 is equal to M2U2. And assuming that this gas is an ideal, so I can write that PV is equal to MRT for an ideal gas. And as well as we all know, for an ideal gas, enthalpy is a function of temperature, which is written like CPT, and internal energy is also a function of temperature, which is written as CVT. So I can write this equation as this equation, because this has Mi has been replaced by M2 minus 1. So now solving this, P2V upon RT2 minus P1V upon RT1 into HI will be CPTI plus M1 will be P1V upon RT1 into U1 will be CVT1 is equal to, what is M2? It will be P2V upon RT2 and U2 will be CVT2. Now the question is, why I am keeping this volume constant? Why I am not saying P2, V2, P1, V1 like this? The reason being, look here, this control volume is having volume V, which is not changing with respect to time. Hence, the volume will remain constant. That's why V. So this V will cancel out. At the same time, this R, which is characteristic gas constant for this gas, this will also get cancelled out. So we will get this, that P2 by T2 minus P1 by T1 into CPTI, and this T1 will also get cancelled out, this T2 will also get cancelled out. So we will get P1 CV is equal to P2 CV. So dividing this whole equation by CV, you will get, and now what is the CP by CV? It is gamma, adiabatic exponent. So P2 by T2 minus P1 by T1 into gamma Ti plus P1 is equal to P2. So P2 by T2 into gamma Ti will be equal to P2, bringing this that side, minus P1, and this is minus. When but this side will become plus, so it will be gamma Ti by T1 into P1. Dividing this whole equation with P2, you will get gamma Ti by T2 is equal to P2 minus P1 gamma Ti by T1 P1 divided by P2. So this will become 1 minus P1 by P2 plus gamma Ti by T1 P1 by P2. Taking P1 by P2 common from both hands, we will get P1 by P2 gamma Ti by T1 minus 1. So this will be gamma Ti by T2. So what is required in this particular problem? It is required that what is the final temperature of this control volume, that is T2. So the final temperature of this control volume will be gamma Ti by 1 plus P1 by P2 gamma Ti by T1 minus 1. In this way, we can solve engineering problems with the help of steady flow or unsteady flow energy equation. Hope that you have understood whatever I have taught today. Thank you for your patient hearing. If you like my video, then please do subscribe.